So we're recording now, so we can start this session. Okay, as I've written today in the chat of this session, I've uploaded all the material we've used so far and the material we'll use today in Aula CESGA, that is the e-learning platform at CESGA. You have the link here in the chat. And so I assume here you should be able to see something similar to this last part here. Can you please check if you can see these 5 files, these 5 PDF files? In Aula CESGA, you have the link in the chat of today's session, but well, the link is aula.cesga.es, and you should, I assume, you should use the Finisterrae to log in your username in Finisterrae and your password, but I'm not sure. You can try and tell me if it works.
We can see.
Okay, so try to access, just to be sure everyone is able to obtain the material. That way that you have centralized all the material here. I've forgotten to, I think, I have to add some links to the GitLab repositories we've used in some of the sessions. Some of these repositories are already in the slides, but I'm not sure if everything is there. So I'll review that and add the corresponding links. Okay, yeah, the documents is the important thing. The other stuff you're seeing here is the organization we use other courses with all the material in different directories or folders. But this year we're just using this plain hierarchy. And I've updated this 0 file, this course outline and first task, with a let me check if this is working. Okay, so in this file is the slides Diego used the first day to present the course, and here I've updated the delivery, the deadline for the first task. Remember, tomorrow is the deadline, so try to upload your work. Basically, you have to follow the instructions in this form. So you have a form in which you should provide your the repository with your solution, so GitLab or GitHub or whatever remote repository. The important thing is that you have here your current version. It's just a sequential version that works. With works, I just mean that it's able to compute the algorithm, the computation of the solution for the equation system. And well, I provide here the corresponding text regarding why you've chosen this method. Well, all this stuff. It's important that you add both Diego and me as co-maintainers of your repository. That way I can access your commits and review your work. Here in the form, the text just says that you should add Diego, but please also add my user. You can find my user also in the document here. Let me go back here. I put here my email in GitLab is this one, but well, probably you can look for my name, or maybe you can find my user in GitLab. If you're using GitHub, I think I'm not using the same address, I'm not sure. But well, let me know if you are having problems to add me or Diego to the repositories. Okay, is it clear? Any doubt with this? Any doubt with the task? Have you already completed the task? Yeah, okay. Anyway, you have until tomorrow to upload it. And on Thursday, I'll give you the second task that is just some additional work on the same code. The idea of the second task is that you profile your code. So basically, first benchmarking your code, having a look at the results with different compiler optimizations. Try to vectorize some loop, depending on what the compiler is telling you, and fill out a table with this information. That's basically the second task. I will give you the details on Thursday. After this second task, we'll give you a period of days for this. The last task is regarding the use of the Intel profiling tools. Diego will show you in the next sessions next week, starting next week. So that's basically the three tasks. The three tasks will evaluate for one part of your grade. Okay, so regarding the different stuff we've seen so far in these last sessions, let me recover block 3 of slides we've used in the last session. If you remember, last week on Thursday, we've seen some basics about the use of make and CMake. And regarding CMake, in the slides, I included some exercises. So my question now is if you tried these exercises or if you had any problem. It's an optional part, so you are not. So it's not compulsory to try and finish these exercises. But just in case any of you have tried these exercises and maybe found any issue or problem with them, just let me know if you need any help with this. The idea is that you create your own CMake for, in this case, for this project. That was an example. But you could also create a CMake for your own repository for the task 1 and task 2, I mean. So if you try it and you find any issue, any problem, just let me know. Okay. Any experience with these exercises? Any of you, sorry, do any of you want to comment something about these CMake exercises? Any problem? Anything to say? Okay. Okay. So then we move on today to the next block of slides. You can find these slides in the chat and also in Aula Cesga. And in these slides, we'll start to see how to characterize the performance of an application. And we'll see some basic performance measures, some metrics to measure performance, and one very interesting way of characterize the performance of an application in a specific platform that is called roofline model. So this is basically what we'll see in the first part of this session. So in this slide, you can see the typical performance metrics you can use in a computer. when you're executing your software, your programs, you can measure basically the performance of CPU, the memory system, and the input-output system. That means the hard disk, for example. And this is a specific case. Of course, the cache is part of the memory system, but well, there are different metrics we can consider for cache. So for CPU, the typical metrics are MIPS. I don't know if you are familiar with MIPS. MIPS means millions of integer operations per second. Instructions, sorry, it's not integer, it's instructions per second. I need to set up here this one to be able to erase without this. Okay, millions of I think Diego told you about this in the first session. You probably don't remember it, but in block 1, let me check block 1 here. In the first session, Diego probably told you about MIPS. I think, maybe no. Yeah, here it's actually the same slide here, MIPS. So basically, MIPS is just a metric that is giving you the number of instructions the machine, your computer, your CPU is able to execute per second. So instructions per second in millions. That's the first letter. Actually, it's not a very popular metric because in the end, some instructions are more expensive than others. So just instructions is not a good metric, above all in scientific environments, because most of the scientific applications programs have an intensive use of one specific kind of instructions that are the floating point instructions. Floating point instructions are the instructions that are computing with floats, with real numbers. You are familiar with float and double, I assume, that are the real number data types you have in C and C++. This is for 32-bit real numbers, and this is for 64-bit real numbers, simple precision and double precision. So floating point instructions are more expensive, and floating point instructions are quite important in scientific codes. So MIPS is not very popular, but the next metric here is exactly what we need if we want to measure the performance of floating point of operations. So flops actually means floating point operations per second. So it's just specific to this kind of instructions, floating point. So instructions that are computing floating point numbers in a CPU. Usually, we can find this with this prefix that just means thousands of millions. So, 1,000 of millions, gigaflops. So giga floating point operations per second. Well, the third metric to measure or regarding the performance of a CPU is probably not so popular, but it's very interesting, and we'll use today this in this roofline model stuff we'll see in a couple of slides. It's called a computational intensity or arithmetic intensity, and basically is giving us information about how much are data used when we fetch this data from memory. So we, in the end, when we are computing in the CPU, so the CPU is the processor of our computer, when we are performing computation, we are taking data from memory and perform any kind of computation with this data. So this is a ratio. We are here comparing how many floating point operations we're doing with this data we're taking from memory regarding how much data we're taking from memory. So this is a ratio. It's from a good performance point of view, we want a lot of computational intensity, a lot of arithmetic intensity, because that means every byte we're taking from memory to the CPU is being computed a lot. So we're performing a lot of computation with this data before getting rid of that data and bringing new data. So the idea is we are interested in high computational intensity, because that means we are exploiting our CPU with our data. If the computational intensity is very low, in the end, we have a lot of transfers between memory and CPU, and very few computation, and that's bad for performance. So that's basically the idea of this metric. Do you understand this concept, computational intensity? That is measured in flop. Flop again is floating point operations. So this is floating point operations, but here instead of per second, per a unit of time, this is per byte. Per byte we're taking from memory. We'll see some examples regarding this. Okay, so these three are metrics that allow us to have an idea about how good is the performance in our CPU. Other metrics here are regarding memory transfers, basically. So we're accessing memory to take data for computing this data in the CPU. So the latency is the amount of time we need to take something from memory to the CPU, and it's just measuring in time units. Okay, and the bandwidth, or also known throughput, is just the amount of bytes we can move per second. So this is a velocity. Is the velocity of our data when we are moving data from memory to CPU. So these two are the typical metrics to know the performance of our memory when we are accessing memory. So a low latency is good and a high bandwidth is good. When we are accessing memory, you know what, then we have our CPU here. The CPU is executing instructions like an addition, and these instructions are using data that is our memory. Our data is on memory in different locations in our memory. You know, we have in the middle the cache memory, that is a faster memory that is used to improve the performance, because memory is quite slow comparing to CPU. So this cache memory allows us to have the data we probably need in a faster space. So here, you know, actually this cache usually in the end are different levels of cache with different sizes and velocities, but well, simplifying, this is just a faster level of memory, and when the CPU needs one data from memory, instead of looking at the memory, it looks at the cache. If this data is in cache, we have a hit. If this data is not in cache, we have a miss, and that data should be taken from the slow memory to cache and to the CPU. So this is one important metric to characterize a code, a loop, for example, or well, a code in general, is the rate of misses or hits in our cache. So that means the number of misses or the number of hits we have per memory access. So a high miss rate is bad because we are missing a lot of data that should be in cache but is not in cache. So we need to access our memory that is quite slower comparing to cache. So that's the meaning of miss rate and hit rate. Any doubt with this? Are you familiar with these terms? Miss rate, hit rate? Sorry? Yeah. Mm-hmm. What do you mean? Yeah. Yes. Yes. Okay. Okay. So, how to measure the performance of parallel applications? Probably you're using this in parallel programming. The speed up is the typical metric for parallel applications, and basically means the performance gain we're having. So how better is the parallel code regarding the sequential code? But well, in the end, we can use the speed up for also comparing between sequential codes. In the end, the idea of speed up is to put here in the upper part the slowest code, and at the bottom here the fastest. So we get how much fast, sorry, is the new version when we are improving a sequential version, for example. So for example, using compiler optimizations, if we put here the code we are optimized with -0.0, and here the code we optimize with -0.2, we should we are obtaining the speed up of this new version. So we know how these two versions are compared. The speed up is above all used for parallel programming. So in that scenario, we're using the sequential time here and here. The parallel execution time we're using with the number of processors we're using, for example, 8 or 32. Ideally, we want a speed up that is, if this is the number of processors we're using, and this is the time, we ideally want a speed up that is similar to the to this line here. That means a linear speed up. Usually, we get something more similar to this. And our code, when we are increasing the number of processors, 4, 8, 16, 32 processors, usually our speed up somewhere during this graph starts to decrease, and we get usually a flat line in some part. So we're reaching like a limit in the performance. This is the usual scenario, but well, depending on the problem and our parallel version, we can get very good speed ups in a lot of applications. Well, another metric similar to speed up is the efficiency. In the efficiency, we introduce the number of resources, the number of in the case of processors or cores, the number of processors we are using to get that speed up. So if we are computing the speed up for 8 processors, here in the efficiency, we put the speed up here, and here we divide by the number of processors. So ideally, the speed up should be near to 1. one speed up would be usually the optimal. In some cases, we can efficiency. Sorry, in some cases we can get efficiency higher than 1 if we are getting speed ups better than the linear case. So we get an efficiency that is higher than 1. But the usual case is that our efficiency is like this. We want something similar to 1, and usually we get something like this, and our efficiency is usually decreasing when we're using more and more processors, cores.
When you see a number of is the number of trees on
Is the number of
trees?
Of threads? What do you mean? Threads. Ah, okay, sorry. Yeah, it depends. The number of threads can be the number of processor or not. It's not the same. Usually, imagine if you have a CPU with 4 cores, that means we have 4 different processor cores in the same chip, in the same CPU. Usually, the CPU should work reasonably well with 4 threads. But you can also use 4 threads in a CPU with just 1 core, but your performance will be worse. So it's not exactly the same. So the number of threads is usually related with the number of processors or cores you have in your platform, but well, you can use more threads. But regarding your question, yes, you can use here the speed up. For example, if you are executing in finished array node, I'm not sure right now, I think we have 24 cores per node. So usually, for example, using OpenMP, you could use 24 threads to try to exploit our nodes. So I suppose that's your question in the end. So yes, it's regarding this. So you could, if you are executing your code, your parallel code with 24 threads, and you compare the execution time with the execution time of the sequential code, you get the speed up for this new version, for the 24 execution. If you divide this time by the number of processors, in this case by the number of threads, if you want, you get the efficiency. Yes. Okay. Scalability. When we are increasing the number of threads and the number of processors, usually we want that our code, the ideal case is that our code is scaling with this increase in the number of resources. So here, usually we can measure this scalability. So that means how well is behaving our code when we are increasing the number of threads in 2 different ways. One is called strong scaling or strong scalability, and the other weak scalability. The strong scalability or strong scaling means that we are fixing the problem size even though we are increasing the number of resources. So imagine I'm multiplying matrices or resolving a large equation system, and I execute the code in 1 processor, in 2 processors, in 3 processors, in 4, in 32, in 64, in 128. I'm increasing the number of processors, but the problem size was all the same. So we are not increasing the problem size. So, of course, we are reducing the execution time, usually or ideally, with something like this, because we are employing more computational resources on the same data. So we are not increasing the problem size, so the execution time should decrease, ideally. Usually, instead of this, we'll probably in some part start to get stuck to something like this. So even increasing the number of threads, we are not improving the time, and sometimes even can be worse. The other concept, weak scaling or weak scalability, means that we are also increasing the problem size. So if we are increasing both the problem size and the number of processors, the number of threads, and we get something like this, that is the ideal case. That is very good. So we have more processor, more computational resources. We have a greater data size, and we have something like this. So we're increasing the data size along with the number of processors, and we get something like this. So this means good weak scalability. Sometimes when we are analyzing parallel implementations, we want to have both analysis, the strong and the weak scalability, to know how our code is behaving, how our parallel code is behaving. You understand the concept of scalability? Any problem, any doubt?
I didn't understand the weak scalability. Can you explain please?
Yeah, of course. I mean, in the strong scalability, we're increasing the number of threads, the number of processors we're using. So imagine we are multiplying. Imagine we are multiplying matrices like this. This is the size of my matrices. So in strong scalability, I start multiplying these matrices one with one processor. After that, with 2, with 4, with 8, with 16, and I obtain this graph here. With weak scalability, in addition to increase the number of processors, we also increase the size of our data. So this for one proc, for 2 processors, imagine I'm doubling my matrices. For 4, and multiply the size of my original matrices by 4. So we increase both the computational resources and the data. So there are different point of views regarding scalability. In the first case, we want to decrease the execution time, increasing the number of resources. And in the second scenario, we want to be able to work with larger data. So we are increasing the resources, but with the objective of increase the number of data we are processing. So both perspectives are interesting and are different. Did you understand? Okay.
So for the first one, we are increasing the number of processors, and the second one, we are increasing the data.
And the number of processors also. So in the first case, we are only increasing the number of processors. So we have a data size that is fixed in size. So for example, in your code for task 1, you are solving a linear equation system. If you are using if you program implement a parallel version of your code we're not doing parallel programming in this course, but for example in your parallel programming course, and you are using the same data when you are executing with different number of processors, you are doing a measure of a strong scalability. You are seeing how well your code is scaling with this perspective. So you're ideally decreasing the execution time because you are using more resources. In some point, probably your improvement gets stuck and you get something probably flat. That's the usual scenario. Ideally, you get something like this, a line like this. In the other approach, weak scalability, you are both increasing the number of processors and the size of your problem, of the size of the data you are processing. So that's the reason why ideally you get a constant execution time. This is the ideal scenario. Usually you have here like a zigzag and probably descending or increasing, sorry. Probably your execution time in some point is not so good, even though you're adding resources. So probably you have something that is increasing. Because
any relation between the number of discussed and the number of children when we use when we are doing scaling? For example, if you multiply by 2, the number of processors is 6 or it's Is Olivia for
I think I understand your question. Yeah, the idea is that you increase in the same quantity the data size and the number of processors. So if you are doubling the number of processors with a weak scalability, the idea is that you double the data size. Yeah, the data you're processing. That's the idea. Because the idea is that if you were able to manage this data size with these processors, if you have the double of processors, you should be able, ideally, to work with the double of data. So that's the idea of scalability from a quick scalability perspective. Okay, so when we have a code that is being executed in a machine, and we want to improve that code, first it's important to characterize that code. That means basically to find the bottleneck or the dominant bottleneck. Usually we have different bottlenecks in one code, but probably one bottleneck is the most relevant. That means that even though we improve some parts of the code, this dominant bottleneck is preventing to actually have a better performance. So we should find the dominant bottleneck. So some codes are dominated by computation. That means that even though we improve memory access, here the bottleneck is the CPU. So is the amount of computation we are executing. This is the ideal case. The ideal scenario is to deal with compute-bound programs, because that means, for example, just increasing the number of CPUs, of course, or buying a faster machine, we have better performance. Because so this is the ideal scenario, to have a CPU-bound program, a CPU-bound code. But sometimes instead of having a compute-bound code, so a code whose bottleneck is the CPU, the amount of work the CPU is able to perform, we have a memory-bound program. This means that here the problem is not the amount of computations the CPU can perform, but the access to memory to have to feed our CPU with new data. So we're not able to feed the CPU fast enough because we have a lot of memory accesses. This is related with the concept of arithmetic intensity. If we have good arithmetic intensity, we are performing a lot of operations with the same data, so we are not accessing new data until we have performed a lot of stuff with the current data. That way we don't need to access new data so often. So memory bound usually implies that we should improve our algorithm, or that we should improve the memory access in some way. And related with this, one memory bound problem is when we are accessing cache. Remember, cache is the intermediate memory here. So we are accessing memory. That's bad because we prefer to just access cache. If we have a lot of cache misses, we have a bad performance. So that's regarding with memory access. If we have a memory bound code, sometimes this is due to a bad cache behavior. So we should try to improve the cache behavior. How? Usually, having a look at the access pattern. If you remember, it's not the same to access, for example, elements that are contiguous in memory. Imagine I'm accessing contiguous elements in memory. This is better than accessing elements that are not contiguous in memory. Why? Because from a cache point of view, some scenarios like this, in the end, means we have more cache misses, because of how cache actually works. That is, taking blocks from memory to cache, and these blocks are compounded by contiguous data from memory. So if our access are to contiguous data, probably we have already the neighbor of our previous data in cache. So that's the idea. So improving the access pattern is important to reduce the number of cache misses. So our code can be so the bottleneck of our code can be in the CPU. So we talk about a compute bound program or code. Can be the memory, a memory bound or a cache bound code, or of course, if we need to work a lot with data that is in a disk, it's not in memory, because imagine we are processing a lot of information that we cannot have in our memory. So we are accessing the disk is really slow. So we in this scenario can have an input-output bound code. This is not so frequent in our in HPC. So of course, in terms of velocity, the CPU is the fastest element in a computer, and the input-output system is the slowest. In the middle, we have the cache levels. Each level is faster than the next one, and the plain memory, that is the RAM in a computer, the read-only memory, the random access memory, RAM, is definitely slower than cache, but far faster than input-output. So regarding now putting some of these concepts all together, we have the roofline model. The roofline model is a way to characterize a platform and the code we are executing in this platform. So basically, it's a graph with this that looks like this. I don't know if you are familiar with this, if you've seen this previously, sometimes. So the graph at first sight is a little bit complex. I will explain the three basic aspects we have in this graph, because it's putting together three different concepts regarding these previous slides. So let me try to let this start. So we're using sorry. So we're using these flops here, so floating point operations per second, and we're also using floating points operations per byte in the roofline model, along with the bandwidth of our memory system. So there is three concepts are put together in one graph, and this graph, just looking at this graph, we have a perception of how good is our code and what improvement opportunities we can find in this platform for our code. So here are the three measures I've just commented. So gigaflops per second, that means the machine peak performance. This is the gigaflops per second. That basically means the how fast our CPU can process data. So this is the maximum velocity our CPU is able to process data, and is measuring gigaflops per second. So thousands of millions of floating point operations per second. So this is the maximum, the theoretical maximum of a specific platform. This horizontal line here. So we cannot have more computations per second than this for floating point operations. It's impossible, because that's the theoretical ceiling of our CPU. This other line here this diagonal line, is the velocity of our memory, and is measured in bytes per second, usually gigabytes per second, because our memories are quite fast. So gigabytes per second is the velocity, the bandwidth, the throughput of our memory. That means the amount of data, of bytes of data we can access per second in memory. And finally, in the x-axis, we have the arithmetic intensity. So this one here. Computational or arithmetic intensity. That means how many floating point operations we are able to execute per byte we are taking from memory. So these two lines colors. Okay, here. So these two lines, the horizontal one here and the diagonal line here, are lines that are characterizing the platform we are using for executing the code. So the platform we're executing our code on, the machine. And the arithmetic intensity is related with our code, with the code we're executing here. Usually with some specific part of the code. Imagine a loop that is consuming most of our execution time. We're interested in see how much arithmetic intensity we have in this loop. We'll see now an example of how these three things are computed. So, looking at this graph, if we have an arithmetic intensity of 4, this basically means that each byte we are taking from memory to the CPU is used in 4 different floating point operations. And that is, well, that is quite that's actually a good arithmetic intensity. It's a very good arithmetic intensity. And with that arithmetic intensity, we have a limit in the performance we can reach that is delimited by these two lines here. If our arithmetic intensity is poor, like imagine an arithmetic intensity of just 0.5, this one. That means the performance of our code, instead of being limited by how fast our CPU is, will be limited by the bandwidth of our memory, and that's the worst scenario. So usually we want to move in arithmetic intensities in this part of the code. So we want that our code is compute bound and not memory bound. How to get this? Well, we'll see now in some examples how we can improve this. But it's more or less clear, the idea of the roof line model. This is called the roof line model because in the end is marking the ceiling, the maximum possible performance in a specific platform. So these numbers are different depending on the platform. And the arithmetic intensity is depending on the application, the code we're executing on the platform. Okay, I'll explain this in the next slides. I don't know what's the difference between these two slides. Okay, here we have a different, I wasn't seeing the difference. So here in this, as you can see in the same roof line model graph, here I have just this line that is marking the compute bound and the memory bound regions, and we can use the same graph for different codes. We can characterize different codes in the same platform, just with different vertical lines. So in this case, we have one code here that is memory bound, another code that is compute bound in the same platform, because in the end, this depends on the code we're executing. Of course, we can use the graph for different parts of our code, and some parts of our code can be compute bound because we have a very high compute intensity, arithmetic intensity, and other parts of my code can be memory bound because we need to access memory to take data, and we are using that data in the CPU for a really few quantity of instructions. So in the end, we have a low arithmetic intensity, and that means we are falling in the memory bound part of the roofline model. So the roofline model is a good tool to characterize our platform and the codes we're executing on that platform. Okay, some examples. In this slide, I'm explaining how to compute the machine peak performance. The machine peak performance is this line here. So it's the maximum performance the CPU is able to provide. How can we usually obtain this data? Well, we can obtain this data usually from the manufacturer. Manufacturer doing the processor, so that we can use the flops. The Intel, for example, is providing the numbers, the data sheet they are providing for the processor, and we can use that for computing this graph. But we can also compute that theoretically using numbers like this. I'm doing here an example of how to compute this by hand, so just taking into account how a model processor works. Or we can also measure this machine peak performance executing some kernels that are designed for computing this. So executing these kernels, we obtain this number. But we have here more or less the theoretical limit in modern processors that is usually between 10 and 100 gigaflops per second. That usually means this from 4 to 64 floating point operations per cycle. You know that a processor has a clock and is executing some instructions each cycle. So we can execute between 4 and 64 floating point operations each cycle. So here's an example. When we are executing FMA instructions and, well, in general, SMID instructions. Do you remember what SMID instructions are? Vector instructions are, for example, SMID instructions. That means instructions that instead of perform a computation for just one scalar, for one data, is performing a computation for multiple data at the same time. You remember vector instructions. So with vector instructions, we are improving the performance of we are obtaining. FMA, sorry, are a specific type of vector instructions. Basically, FMA are fusion, multiply, and addition. That means it's an instruction that is, I'm taking this example. Imagine this. This is a matrix multiplication. And here, to perform matrix multiplication, we are performing a product. And after this product, we add the result with other number. So this is a product. And then addition is something, if we have this FMA instruction in the instruction set architecture of our computer, this only instruction is able to perform these two operations in the same instruction. So that's the optimal scenario. Mother architectures have these FMA instructions, and mother compilers are able to exploit these FMA instructions. So in this example here, I'm assuming we have FMA instructions. So how to compute the maximum number of floating point operations per second? Well, first, we take the number of cycles in our CPU. So that's the frequency. In this case, in gigahertz, giga cycles per second. In modern Intel architectures, we can execute 2 FMA instructions per second per cycle. So we can use because we have 2 FMA. Well, this is related to how the CPU is designed, but we have 2 FMA units. So 2 FMA instructions in the optimal case. In the end, these are just lab conditions. So in the end, we are not getting this performance never. But well, this is the optimal theoretical optimal case. So we can execute 2 FMA instructions at the same time. So we are able theoretically to execute 2 operations like this at the same time in the CPU, 2 FMA instructions. Each FMA instructions, each of these 2 FMA instructions is dealing with this AVX. Do you remember AVX? What is that? AVX? Okay, I can take back here. If you remember from the block regarding the compiler, in the vectorization part, I told you what a vector instruction is. These vector instructions are exploiting some special registers we have in our CPUs that are larger than the usual registers. In a 64 machine, we have a lot of 64 registers, but these vector instructions are using other special registers that are larger. So, for example, in finished array, we have AVX2 registers, and AVX2 registers are registers that are 256 bits long. That means if one integer is 32 bits long, how many integers we can pack in one of these large registers? Well, 256 divided by 32. So this is this operation here. So this is the number of integers, well, in this case floats, because floats are also 32 bits, sorry. The number of floats each FMA instruction is computing. So this is a vector instruction. So in this case, these vector instructions are working with 8 floats. So we have 2 simultaneous FMA instructions working with 8 floats each of them. So this 8 multiplied by 2 multiplied by the frequency of our processor. And if we are working in a multi-core node, like for example in finished array, this is an example for finished array that has 24 cores per node, so we can multiply the previous number by 24. If we are in a machine that just 1 core, this would be the theoretical maximum. So it's more or less clear this expression. I know this is a little bit complex, and usually you don't need to do this because you have other ways to get this number. For example, with Diego, you'll see how Intel advisor is able to compute this number, just executing some kernels and obtaining this theoretical ceiling or maximum performance of CPU in the computer, in the platform. Okay, so in this specific case, regarding Haswell, we obtain this number of gigaflops per second. So this is the maximum number of operations with floating point numbers our CPU can execute in finished array. And this would be this line here. Well, of course, this line is like this, but then we mark here the limit with the bandwidth our memory is able to manage. So we have the line regarding CPU. Now we compute the line regarding memory. The memory bandwidth, so how fast our platform is able to move data from memory to CPU, is something that is regarding the RAM memory we have. So again, you don't need to memorize this number. In this specific example, I'm using just one socket of memory. So we have just one module of memory. this module is of technology DDR4, so that means a bandwidth according to the numbers, to the data sheet of this memory of 2040 bytes per second. Since FMA instructions are accessing, these memories, can provide us 8 bytes per memory access. We multiply all this and we obtain the velocity of our memory, the bandwidth our memory is able to provide. Again, there are kernels specifically designed to test this throughput, this performance of the memory. With this, we obtain the bytes per second. These bytes per second if we multiply bytes per second.
Why does the line don't hit the 0.00?
Here, you mean? Why is not here?
Yes.
Yeah, okay, now I will explain this. It depends on the platform. Sometimes it's here and sometimes it's here. It depends. How the question is, okay, now I've obtained it's a good question because so far we have obtained this line here and we know the velocity of our memory, that is this number in gigabytes per second. So we have the gigabytes per second, sorry. I have a lot of problems to write here. So we have the gigabytes per second, that is the bandwidth or throughput of our memory. So if we put in the x-axis the different potential arithmetic intensities for our code, in this case, usually the usual approach here is to use logarithmic scales, both in the y-axis for the gigaflops per second of the CPU, so for this, and also in the arithmetic intensities, typical to the use of a logarithmic scale. But anyway, the important thing here is, here in this x-axis, we have the arithmetic intensity that is measured in floating point operations per byte. So this is floating point operations per byte. If you multiply gigabytes per second by, so if you perform this, I'm going to put here this here, so you divide your bandwidth with the different floating point per byte, you get rid of this. These are bytes. So in the end, you get your giga. Think about this. Sorry, it's not a division. That was the problem. That's the reason I didn't understand this. Let me rewrite this. So we have our bandwidth, gigabytes per second, and we multiply that by the arithmetic intensity, that is floating point operations per byte. And now you get rid of the bytes because this is multiplying and this is dividing, and you get the gigaflop per second. So this in the end means we are attaining the gigaflop per second. That is this line here. So gigaflops per second is basically the same quantity we have here. So when we reach the number of gigaflops per second, that is this line, we know where to put this diagonal line. I don't know if you are following my explanation now. regarding your question, multiplying the bandwidth with the different flops flop per byte, you obtain the gigaflops per second, and if you obtain the same value you have in this gigaflop per second, that is the limit. That way you know where to put this. This is always a 45-degree diagonal. So once you meet with this computation, this number, the number of this, you have this here, you put this line here. And that way you have the limit in both bandwidth and computation. Have you understand it? Have you understood? Okay, any doubts regarding this? Are you following the explanation? Can you hear me through the video conference? Can you see the slides and the explanations on the slides?
Yeah, I got it.
Okay, thank you. Okay, so this is how you basically compute these two numbers, the ceiling and the diagonal line that is also limiting the memory bound part. So the final part is to analyze the arithmetic intensity of our code, to know where to put this vertical line in the graph. So now, so far we have this graph that is just compound of the ceiling, the maximum numbers we can have. So now we need to put in that graph parts, regions of our code, or the whole code. It depends on our analysis. Here, for example, in this example, we have the arithmetic intensity of a matrix multiplication. So we have matrix multiplication, and here we are performing the arithmetic intensity of that. Again, we can perform this, but we can compute this, sorry, by hand, just take using the numbers like in this slide, or usually some tools are computing this for our code, like Intel Advisor is doing. In this case, it's very easy to compute. This is a very simple example. So we have these loops, and the computation in the end is like this. We are with this is a matrix multiplication, so we are multiplying scalars and adding to accumulator in an accumulator. So we have, remember, arithmetic intensity means floating point operations per byte. So to compute this, we need to know how many floating point operations we're performing. So here we're performing a product, a multiplication, and here we're performing an addition. So we have two floating point operations, product and addition. How many data we're using to compute this? We need to access A, this is a read memory operation. We need to access B, we need to access C, and we need to write again on C. So we have 3 reads and 1 write operations. So in the end, we have 4 data transfers and only 2 floating point operations. So this is a low arithmetic intensity. We are moving a lot of data for a relatively low amount of computation. In this case, this means, sorry, this is for data. How we translate these 4 data in bytes, where these data are float numbers. So float numbers means 4 bytes per float. So 16 bytes. So the ratio is 2 floating point operations per 16 bytes. You have here the result. So this is the arithmetic intensity for this specific snippet of code, and it's a relatively slow, for a relatively low arithmetic intensity. So if we put this in our, if we put this arithmetic intensity in our graph, our graph here. Well, this graph is not for this example. Sorry, I don't have the graph. I think no. Well, I don't have the specific graph for this case, but probably our example here is memory bound because we have a very low arithmetic intensity. So even increasing our, even improving our code, we are hitting a limit that we cannot pass. So how to improve this scenario? We need to improve the arithmetic intensity. For example, using looking at the cache hits, misses. If we are dealing with a relatively high amount of cache misses, that means we are accessing memory more than we should. Because in the end, in this computation, I'm assuming all our access to memory are real accesses to memory and not to cache. If some of this data are in cache, we are not accessing memory for this. So we are reducing the memory accesses and we are improving the arithmetic intensity. So looking at the cache numbers, how the hit ratio or the miss ratio, we can know if we are actually in this scenario or if we are here, for example. So we should look at the cache behavior. If the cache behavior is bad, then we have this opportunity to improve our code, just improving the access here. If you remember from our previous session, here this access of this pattern of accesses to memory is terrible usually. So just interchanging these two loops, usually we improve the pattern, the memory access pattern that translates in a cache behavior that really improves. Now I'll show you the execution times for this change. And in the end, that means a higher computational intensity and the opportunity to improve more our code because we are moving from one part that was memory bound to other part of our graph that is compute bound. So we have a higher ceiling. So we have more opportunities to improve the code. Any question? Any doubt? Tell me.
The next slide.
This one?
Yes.
Let me.
When we say we count N, the matrix A, the matrix B, and the matrix C. That?
Yeah, we are multiplying A and B.
Now when we say 4 bits, the last
What do you mean, 4 bytes?
Yes, 4 bytes.
This one?
Yes.
This is because in a 32-bit machine, or even in a 64, in a 32 or 64-bit machine, the size of a float data is 32 bits. That means 4 bytes.
Is not the number of data.
Is the size of our data, of the data type, sorry. So we have floats here, and floats are 4 bytes long. So each float means 4 bytes of data we're moving. Since we are moving for data because we have 3 reads and 1 write, so we are reading 3 times from memory and we are writing 1 time in memory. In the end, we are transferring 4 data, 3 reads and 1 write, and each data is 4 bytes per data. Each transfer is 4 bytes per transfer. So in the end, that means we are moving 16 bytes. And we are only executing to floating point operations. How can we improve this? Reducing the number of memory accesses, exploiting our cache. So we should look at the cache. Well, here we have I think I have, okay, I have some slides about how to improve this specific example. Before that, the roofline model can be expanded with different new ceilings, with new lines, depending on different scenarios in the same platform. For example, here you have 3 examples taken from Wikipedia, but you can find, usually when you are seeing a roofline model graph, you have different lines here. For example, these 3 different diagonal lines are assuming that, for example, you don't have a prefetching in your hardware, or you don't have a NUMA. I don't know if you're familiar with this word, NUMA, non-uniform memory access. So maybe in your computer you have some memories that are depending on your memory address your access is slower. So in these different scenarios, your bandwidth is even worse. It's even worse. And here you have different limits for the CPU performance. Imagine, in this case, these are examples, are different scenarios. In this scenario here, we have a limit when we have a instruction level parallelism and task level parallelism. You remember, instruction level parallelism means that our computer is able to execute multiple instructions per cycle, and task level parallelism means we have multiple cores that are able to execute multiple threads at the same time. But if we have disabled some of these features in our platform, the limit our code can reach is lower. So we have different limits depending on the features we can exploit in our platform. And here, this is basically what I was commented regarding the arithmetic intensity. How can we improve the arithmetic intensity? Well, here you can see in the here this is the source of this graph from Wikipedia, and here in this graph, different levels of cache misses are being taken into account. So here, the left line, that is the worst scenario here, means we have 3 different, I don't know if you're familiar with the different types of cache misses, but well, this is related with this. You can see this I'll show you this in the Wikipedia page. The roofline model page in Wikipedia is quite good, and you can find here these 3 scenarios. As you can see here, this left line means that we have the 3 typical types of cache misses in a computer: compulsory misses, capacity misses, and conflict misses. But I don't know if you're familiar with this. This is related with how a cache works. You know this kind of stuff? Okay. Basically, compulsory misses in a cache. Let me use this. These are 3 different types of misses in a cache. A miss in a cache in the end is the same. A miss in a cache means, imagine this is my cache with 3 blocks and some bytes per block. Block 0, block 1, and block 2. And this is my memory. And my CPU needs some data. And the first place we're looking for data is the cache. The first time the CPU is using a data, is probably a cache miss because this data was never used before. Imagine we are starting from scratch, our code. So the first data we're taking from memory is not in cache. So that means we have a cache miss. And we need to look for that, the whole block, and we load the whole block in a cache line. That is the name of the blocks in the cache. So this is a compulsory data. We cannot avoid compulsory data usually. The next access, if we have a good access pattern, the next access is probably not a miss because we're taking a whole block of bytes. So the next access is probably a neighbor access, an access to a neighbor data from the previous data. So ideally, this is already in cache now, so we don't have a miss. But when we perform the different computation on all the data in this block, again, we have a cache miss. That is a compulsory miss when we start with a new block. If we perform this multiple times, in the end, our cache is full. So if we need a new data and our cache is full, we have a capacity miss. Because the problem now is that we don't have enough space in our cache for new data. So we need to replace something here and put more data. So some misses regarding capacity can be avoided. It depends on the organization of our cache. And the conflict misses means that even though sometimes let me delete this. Imagine that my cache is empty. Now I take from memory one block, I execute some code that is exploiting this block of elements, but I need a new element that is in other block that is mapped to the same block here, even though the rest of the cache is empty. This happens because of how is the mapping between memory regions and cache lines, but it's regarding with cache, how a cache work. How cache operates. So these are called conflict misses because some blocks, some regions of memory that are mapped to the same memory, to the same cache line are conflicting. So if we are accessing these elements alternately, we are all time having conflicts. So we can avoid this changing how we access this data. So in the end, these two kinds of errors can usually be solved just changing the access pattern to our data. So that's what, in the end, we're doing here. We're increasing the arithmetic intensity, just reducing the number of cache misses. Here we have both compulsory, capacity, and conflict. So the three types of cache misses. Here we avoid, I don't remember which kind of cache misses here. The only compulsory and capacity is here. So we are removing the conflict misses, just changing the pattern of access. And here we are improving even further just by avoiding the capacity misses. So we only have the compulsory misses that usually are really are impossible to reduce. Just the only possibility is to improve our cache. If we have larger blocks in our cache, that's something we cannot set up. It depends on the physical cache, so we cannot improve the compulsory misses. So that's why here the arithmetic intensities improve. So here in the first line, we have a bad scenario because the limit here is the memory bandwidth. So we have a memory bound code, even removing the capacity, the conflict misses. We are still memory bound, but once we get rid of both capacity and conflict misses, just with the compulsory misses. Now we are in the CPU bound part, and that's good because if our real performance, let me take this. If our real, so this is the limit, but maybe our performance is not actually this. It's just, imagine here that this is the real performance of our application. The problem is if we are here in this arithmetic intensity part, this is our real performance. But if we are here, the performance opportunity, the opportunity to improve our performance is just this. But here, if we move here, we have a lot of margin to improve our performance. So that's the important thing here. So here, even though maybe we are vectorizing or whatever, maybe we are not taking advantage of that vectorization, because the problem here is not the CPU, it's being the bandwidth, the memory bandwidth. So that's why with this roofline model, we can prioritize how to optimize our code. Sometimes it's better to work on improving the arithmetic intensity before any other approach. Anyway, with this, you understand the idea of the exploiting the roofline model. If you have this idea of how to improve, here you have a different roofline model, so a different platform. Imagine, in this case, you have these three different ceilings. Here, basically, this is the scalar performance. That means we are not using vector instructions. Here, we're using vector instructions. Remember, vector instructions is one way to exploit SIMD parallelism. And here, this is the line when we have SIMD parallelism along with multi-core. So along, for example, with OpenMP. So in this line, we are exploiting OpenMP and vector instructions. In this line, we are only exploiting vector instructions, and in this line, we are not exploiting vector nor OpenMP. So this is the limit if we are not exploiting these two possibilities. So if we are here, even though we vectorize and parallelize our code, we are limited by this bandwidth. We are not reaching the maximum possible performance in our machine. So we are not reaching this point because the bandwidth is limiting our code. So how to improve this? Well, we need to optimize the memory access to move our line to a region that is CPU bound, because otherwise we are not able, will not be able to exploit the real performance of our CPU. So this is basically the way we exploit this representation, this characterization of performance. Just looking at the graph and at the computational intensity of our code. And this is our current performance. So we can improve our performance, but we have a ceiling that is lower than other ceilings in other parts of the graph. Well, so why this is that is a good tool? Because it's very visual and intuitive. Once you get familiar with this, it's very easy to see at a glance the different opportunities we have to improve our code and how to prioritize the next steps. So here you can see three different applications with three different arithmetic intensities. And of course, the first application is memory bound, and the other two applications are compute bound. And well, that means this application, even though we work on parallelizing, we're hitting this limit and we cannot get the performance that is possible in the other two cases. Well, we have some resources to obtain the numbers for this machine characterization to avoid the manual computations I've shown you in the slides. For example, the InterAdvisor you will use with Diego. is very well. It's a great tool because it's able to perform all this automatically. So you can get the roofline model for your code for different loops on your code. So it's computing all this out of the box for you. So it's very useful that way, and it's even giving you advice of how to optimize your code looking at the graph. So it's a great tool, Intel Advisor. Diego will teach you about this tool in the next week. We have other alternatives to the Intel Advisor. Sometimes you don't have access in your platform. Maybe you don't have Intel Advisor, so there are other alternatives. Not so powerful as Intel Advisor, but well, for example, this tool here. Well, I cannot follow the links in this PDF. Let me use the links to follow this link. Well, this is actually a research group that has a lot of work about this roofline model and is developing an empirical roofline tool that in the end means that this tool here we have access to the repository. It's a Git repository, and this tool has some kernels that allow us to characterize the machine for the CPU peak performance and for the memory bandwidth. So it's able to compute this graph. What else? Let me recover. So instead of manually performing this, that is the hard way. It's not usually very easy. We have some tools like Advisor, and this I've show you. So how to exploit, just finally, how to use all this information to track how you are optimizing your code. Well, usually you can put in the graph the different versions of your code. That way you are tracking how you're progressing. And for example, Intel Advisor is able to do this for you. So can put different versions, different iterations of your code. That way you are seeing your progress in performance from a performance perspective. For example, imagine you're here, and as you can see here, we are memory bound because we are in the part, as you can see here, the CPU bound starts here more or less, and here we're memory bound. So we can improve here just, for example, using vectorization. But we are still bound by the memory access. So how to improve this? This is a real example of matrix multiplication. So here we are performing a real improvement with matrix multiplication just by interchanging these loops. If you remember, this was an example we worked on last week. Just changing these loops and applying vectorization to the inner loop. So something like this, to vectorizing this loop here. So that means we are performing this instead for individual scalar floats for groups of 8 floats using in this case FMA vector instructions. We can have this improvement that is actually a very good improvement with a very naive change. So it's important to track your progress, and this in the roofline model you can track your progress and evaluate if you are exploiting your hardware, if you should try to increase your computational intensity or not. Well, it depends on the situation. Okay, so this is more or less the important aspects of roofline. And I have an exercise for you, but you can have a break now if you want. Okay. So we can have a break of 20 minutes. And after that, or whenever you want, try this very simple exercise. The idea is that you execute this tool, this roofline toolkit in finished array. So that way you can also work to the use of finished array, executing this. So in this exercise, the idea is that you get the roofline model for finished array, just the limits of the platform, not a specific code. So, and this is something that this tool is computing out of the box. You should provide a config file, and you have this config file that is included among the recipes you have with the tool, and you should customize this with the instructions I'm providing here and executing the tool. Okay, well, rest now for 10 minutes, and after coming, try this and let me know your doubts.
Yeah.